Okay, so in the last few videos we have been discussing about different coverage criteria that can be used in logic coverage, and in that context we have studied about active class coverage. And in the context of active class coverage we studied three different criteria. First one was general active class coverage, then we talked about restricted active class coverage, and then we talked about correlated active class coverage. Then we also discussed in the last video about inactive class coverage, and there were two mentionable criteria. One was the restricted inactive class coverage, and the other was general inactive class coverage. So far we haven't discussed about how we can use a definitional approach to make a specific class active in a predicate. So if the predicate, for example, is not very complex, then it usually works by just guessing which value to set for the minor classes to get the active class. But for some complicated predicates, this can be a problem. So how to solve that? We can make use of a definitional approach, which I am going to discuss in today's video. So let's get to the topic. So finding values for minor classes, which we denote by Cj, is easy for simple predicates, but how to find values for more complicated predicates? For that we have a definitional approach, and how that approach works is that we set PC equal to true is the predicate P with every occurrence of C replaced by true, and we also make a predicate PC equal to false, which is the predicate P with every occurrence of C replaced by false. So C is that particular class which we want to make active. So we make two different versions of this class. In one version we replace every occurrence of that class with true, and in the second version we replace every occurrence of that class with false. Then what do we do next? To find values for the minor classes, we connect this PC equal to true and PC equal to false with an exclusive OR. So this is the main result or main formula which we are going to use to find out the values of minor classes to make a specific class active. So in this case, for example, C is the class which we want to make active. So we will replace in one instance, in one version of the predicate, with all occurrences of C with true, and in the second version we will replace all occurrences of C with false, and then we will compute the exclusive OR of both these, and whatever values we get will be the values of the minor classes which will make C true in the predicate. And after solving PC, that describes exactly the values needed for C to determine the predicate. P means how we can make C active in this predicate. So here we have an example, very simple predicate. For example, if we want to make A active, what we will need to do is we will replace every occurrence of A with true once, and in the second instance we will replace every occurrence of A with false and then we will take an exclusive OR of both these version of the predicate. So here is that process illustrated: PA equal to true and PA equal to false. So when we replace with A true, so we make true OR B first version, and we make false OR B second version, and we connect both these with an exclusive OR. So as you know from discrete math, that true OR B is always going to be true, because it doesn't matter what value B has, this part of the expression will always be true, and false OR B will always be dependent on B. Whatever value B has, the result of this right hand sub expression will be B. If B is true, then the result will be true, otherwise if B is false, then the whole thing will be false. So we just write that by B. Now you remember from discrete mathematics that an exclusive OR is always true when one of its operands is true. If both are true or both are false, then it always returns a false. So in this case we already have a true on the left hand side. It means when if this expression exclusive OR expression has to return a or a true, then this must be a negation of this part on the right hand side. So that is how exactly we compute. So here, not when we solve this true exclusive OR B, we get not B, and this is exactly the value that that will make this predicate predicates A class to be the determining class, that is set B to false. If we set B as false in this class, then the whole predicate is now dependent on A. If A is true, it will be the predicate will be true, and if it is false, then the predicate will be false. So that this is how we make a class, a determining clause or an active class in a predicate. So let's have a look on another example. So now we have another predicate in which we have replaced the OR with an and now we want to make A again an active class. How we will do? We will repeat those steps. First, we will create a version of the predicate with A replaced with a true, and another version with A replaced with a false, and we both connect these with connect both of these with an exclusive OR, and then we solve this. True and B, false and B. And from discrete math, you might remember that true and B will be dependent on B. If B is true, then the whole thing will be true, otherwise it will be false. So this part will return a B, and false and B, it doesn't matter what value B has, so it will always be false. So you can write B and exclusive OR false, and as we just discussed in this part of the slide, that if exclusive OR will always return a true when one of the operands is true. So here this is definitely false, so it means we can retain this B, so the result is B. So how we make this predicate, how we make A active in this predicate, we set B to true. So if it is true, now it will depend on A. If A is true, then the whole predicate will be true, and if it is false, then the whole predicate will be false. So that is how we make A class to be an active class in this predicate, and that is known by this result after solving this expression, that B has to have a value true in this predicate. So let's work out another a bit more complicated example. So here if we want to make A as an active class, so we will need to set two versions of the predicate. First is BA equal to true, and then BA equal to false. So we connect both of those with an exclusive OR. So you just see that true OR B and C in the left hand side of exclusive OR, and false OR B and C in the right hand side of the exclusive OR. Now we need to solve these. So since this is an R, this part is an OR, and we know if we get one operand to be true in the OR, it doesn't matter what value the other part has, so we just compute this to have a true value. On the other hand, this is false, so this whole thing will be dependent on this part of the expression, sub-expression, so we just write that B and C. Now we know from discrete math that exclusive OR will always return a true when either one of these operand is any one of these operand is true. When both of them are true or when both of them are false, then it returns a false. So we always get a true here. So we need to connect this with this part of the expression with a not. So that exactly we have done here. Not B and C, or you can simply write not B or not C. So it means we need to make false one of these to make a determining clause in this predicate. So that makes sense. For example, if I set B to false, for example, this whole thing will be false, and when this is false, then the predicate depends on A. If it is true, then the whole thing will be true. If it is false, then it will be false. So that is how we make a predicates class to be an active class, by finding the values of the minor clauses by making use of this approach, which is called the definitional approach. So not B or not C means either B or C can be false. So restricted active class coverage requires the same values for both values of A, and CAC does not. So it means if we want to achieve RAC on this predicate, then we will have to choose the same set of values, because we can make any one of these false, but for wrap we will have to fix that values, those set of values to be the same for when a is true and when a is false. So you can also take help from the tabular method to determine for the determination of the clauses. So math can be sometimes complicated, and some people might find it problematic or maybe confusing to apply those formulas and connecting the two versions of the predicate by means of an exclusive OR and then computing it. So you can take help from the truth table. So here, if you look at this is the same predicate we have been working in some examples in the last few videos, and now we want to find which set of values make predicates clauses A, B and C active or determining for this whole predicate. If we want to make A active, then we will be looking on the entries in this column PA, and if we want to see where B is active, we will be looking at this column, and if we want to see where B is active, we will be looking at this column PC. So for A, if we want to make A active, then we need to find those rows where A's value changes from true to false. For example, if I look at this one and this one and see that the minor class values don't change, but the predicate changes here, so it means here A is actually determining the value of the predicate. So there you see B and C are the same, A differs and P differs, thus TTT and FTT cause A to determine the value of P. Likewise, you can also look at second row where A's value is true, B's value is true and C's value is false, and you can also look at row number 6. Here A changes to false and the minor class values are the same which were in row number 2. So, and the predicate also changes from true to false. It means in these tuples also the change in the value of A is actually determining the value of the whole predicate. So these two pair of rows can also be used to determine the predicate by means of class A. There you see that. Now you can repeat the same thing with row 3 and row 7. Here A changes from true to false and the minor class values are F and T, and the predicates has changed from true to false. Therefore the values of A in this in these tuples which changes from true to false is actually making the predicate to change from true to false. Therefore A is determining the value of the whole predicate by these set of values. Finally, this third pair TFT and FFT also cause A to determine the value of the whole predicate. And the same story can be repeated for clauses B and C. For example, if we want to make B active, on which row I need to look at, I can look at row number 2 where B's value is true and its value changes from true to false. The predicate changes from true to false, and the minor class values in this case are A and C. Their values don't change. Therefore, row 2 and 4 are representing those set of values or providing those set of values in which class B is active. And for C, you can look at row 3 and 4. Here C's value changes from true to false, predicate changes from true to false, and minor class value B and A have the same value, F and F and T and T. So therefore TFT and TFF cause C to determine the value of P. So in this case, if we want to make C the determining class, then we can make use of the values in rows 3 and 4. So in summary, 3 separate pairs of rows can cause A to determine the value of P. Only one pair each for B and C will cause these clauses to determine the value of the predicate. So this concludes our discussion on logic coverage. So we have seen that predicates are often very simple. We thought we've discussed about a study which gave the results that about 90% predicates have around 3 classes, and in fact most predicates only have 1 class, and with only class predicate in a coverage is enough. If you have just 1 class in the predicate, then predicate coverage is enough. If you have 2 or 3 classes, then you can think about using the combinatorial coverage strategy. And in other cases, when there are maybe more than 3 classes, you can think about active class coverage and inactive class coverage for those kind of predicates. And combinatorial coverage is impractical for predicates with many classes, because in that case the number of tuples or rows in the truth table increases exponentially. So that concludes our summary for logic coverage, and in the next video I will be talking about, or I will be in fact demonstrating the demo of this logic coverage web app, in which you will see how we can practically use an application to find out test cases or test values fulfilling different logic coverage criteria. Thank you.